Introduction to Passive House Standard. Now, what is this all about? Well, it's about energy efficiency. What you see on the left-hand side, that is an electric car, which uses about 15 kilowatt hours per 100 kilometers. And this is a factor 5 better than ordinary internal combustion cars. Well, the same improvement, or even better, we can do with buildings. What you see here is a passive house, which was demonstrated already 1991. It's a 15 kilowatt hours per square meter house for heating. And that's a factor 10 better than the average efficiency in average existing buildings. It's a tried and tested technology. Now, does this even matter? Well, this is the final energy consumption in Germany. I'm using that because we know it very well, but it's not so different to other final energy consumption patterns. What we see here is that traffic is indeed the biggest chunk, but another very big part is space heating. That's about 27% of the overall final energy consumption. So traffic and space heating together is already much more than half of all the final energy. Now, what will be the influence of improving energy efficiency here? This we can see from this comparison of energy consumptions in German buildings. We have improved the way we are building from old times with about 200 to 300 kilowatt hours per square meter in here. With each regulation, 1984, it was already in the range of less than 200. 1995, it was even reduced more. And nowadays, it's about half of what we had at the very beginning. But with a passive house, we add another 75% of energy savings. So it's even much less than what we consume nowadays in new constructed buildings. Now, this can be done with available technology, and it has been done for a lot of different types of buildings. What we see here are some single family passive homes, and they have been built in different construction methods. Some are timber based, others are masonry based, others are concrete buildings. But we can also build high-rise passive houses like this one in China, in Gaobeidian. This is a very energy efficient high-rise building, a certified passive house, which was built at that place. And it's not only residential buildings. We can also have energy efficient non-residential buildings built to passive house standard, like this passive house office, exhibition and laboratory building in Qingdao. It's also a certified passive house. It was designed by Rongen architects, especially by architect Michael Tribus. We can apply the technology using passive house efficiency also to existing buildings. And these are some examples of refurbished buildings using passive house components in the German and Austrian building stock. So this is working to reduce the overall energy demand of these buildings by at least a factor 5. Now, how is this even working? In a lot of climates, we have cold winter conditions. This is what we see here in the background. So it's much colder on the outside when we want to have it for comfort at the inside. So now, if we have these higher comfortable temperatures on the inside, just from physics, from thermodynamics, we will have a energy flow from the inside out. This energy flow can be called a loss. So there are transmission losses. These are heat flows through the walls, through the windows, through the roof. There are ventilation losses, and there might even be some other losses. Now, as long as we only have these losses, the temperature inside the building will drop until it reaches the temperature outside, and that won't be very comfortable. So we have to substitute for these losses. And we are lucky because some of the substitution is just for free. We get solar energy through windows. We use electricity inside of a building, and there are persons in the building. So these are contributions to free heat. But it might not be enough to compensate for all the losses. So for the rest of the compensation, we have an active heating system, which needed some fuel or needed some other kinds of energy in order to keep the building comfortable. Now, these two energy flows, the gains and the losses, they have to be the same. Otherwise, the temperature in the inside will change. Let's look at an example. This is an existing building, old building built 1929. It had in the original state 200 kilowatt hours per square meter in a year, and we see the actual energy balance on the right side. So we see a lot of losses through the wall, through the roof, also some ventilation losses. And there are also losses through windows. And these are the gains. So in these existing buildings, the gains are not so very important because the losses are so high. But we can reduce these losses by adding insulation. And this is what has been done in that building. So this is how it looks nowadays with an added insulation to the external wall, with added insulation on the roof, with improved windows. And we could reduce the overall energy demand, in this case, by 87%. You see how much the losses on the wall was reduced, how much we improved windows. Uh, well, we can even check whether this is true because we have measurements of the resulting energy demand in this building. And this is what we see here. The blue bars, these are the calculated energy balance values. And these blue dots, these are the measurements in the first year of that building. So it's actually working. The savings were even a little bit higher than what had been calculated. So how does that work? Well, there are five basic principles how to construct an energy efficient building in a heating climate. And the first and most important principle is insulation, really good insulation. The insulation has also to be going around every corner, so we have to avoid thermal bridges. We have improved windows, passive house windows, which have higher energy gains than energy losses. Of course, it has to be airtight. We have seen during the pandemic why that would be important. And we have enough fresh air for everybody using a ventilation heat recovery system. So we supply fresh air and only fresh air, no return air to the living room, to the bedrooms, and we extract the air where it is most contaminated in the bathroom, in the kitchen. Let's look into these principles a little bit closer. Excellent insulation. That can be done by different types of components. Masonry walls, timber walls, lost concrete forms, and so on. So there's a lot of possibilities how to improve that insulation. And all these things are available on the market. We can also check whether this is working in the way we want it to work. This is on the right-hand side a thermographic view of the improved building. It's the same building I have shown in one of the last slides. And in the background, you see a not insulated building. This is in the original way. It had been not insulated. And you see the contrast. So the temperature on the surface of the insulated building is almost as low as the temperature in the freestanding tree in front of it. Reducing thermal bridges, how do we do that? Well, this can be seen in this slide where you see four versions of the same situation. So this is the architectural design for the refurbishment. This is the calculated distribution of temperatures. This is the actual distribution of temperatures on the internal surface. And this is just a visual view photography in that room. And what we see is that we get even at this part a very high comfortable indoor temperature. So there's no danger for any humidity at that places. The third principles are the passive house windows. Passive house windows are much more efficient than standard windows. Well, we started with the single pane windows, which had a energy loss of more than 33 liters heating oil per square meter. It's already reduced if we use double pane windows, and even more reduced if we have low emissivity windows, which is now mostly used in new buildings. But there is still a loss, and it's still quite high. It's still in a range of 4 liters per square meter a year. But with the triple pane passive house windows, we get net gain windows. So during winter situation, these windows they gain more energy than they lose. We can also see that the comfort in the building will be improved by these improved components. So this is again a thermal view. On the inside, this warm color shows a temperature in a range of 22 degrees. But the window surface is not much colder. It's in the range of 90 degrees. So you can be in front of a window and will not feel any cold perception, which is quite different to existing old windows you see here. So the temperatures can be as low as 12 degrees on the surface. That won't be very comfortable. The ventilation systems provide fresh air, and this will give us good indoor air quality. How important that is, we have seen during the pandemic. It also will help for the right humidity on the inside. It can be a dehumidification if you need that, and it can also humidify the air as we want. The modern systems, they are small, quiet, and efficient. And if you use a mechanical ventilation, you should use an efficient one. And a best way to do is to use a certified passive house ventilation system with heat recovery. Now, there are different climate zones on the planet. The specific way we build a passive house for the different zones is different, whether it's in a cold climate, a warm, moderate climate, or a desert or tropical climate. It can also be built by using materials which are from the agricultural way. So what you see here is a certified straw prefect passive house construction system, which is also already available on the market. So this is solving quite a lot of problems we have today at different parts of the world, because also in China, you even don't know what to do with all the straw which is available from agriculture. Passive houses can be built very affordable. These are examples from the cities of Innsbruck and Munich, where passive houses have been built for affordable housing. And these are within the least expensive buildings which have been built in these cities in the past years. So this is really working. Another example for affordable housing, these are buildings in Philadelphia, United States of America, terraced houses built in a affordable housing project in the US. And if you know a little bit about the situation in the US, you know that this is only possible to build it to that very high efficiency if it's not quite expensive. And it wasn't expensive. So passive houses can be realized for everything you want to build nowadays. These are some examples from different parts of the world. Some of these are refurbished buildings, some of these are new constructions, some laboratory buildings, some schools. So a lot of different tasks which have been realized as passive house. Energy efficiency, like passive house, they have a lot of advantages. You get the optimal comfort we have seen, you get the healthy indoor air, you reduce the total cost of living. It's also a solution for climate protection because the energy demand is only 1/10 of what you normally have. So we can use renewable energy easily to provide everything which we need in these buildings. It will enable sustainable growth in this way, and it will help with participation and comprehension because all of this is very easy to understand. So, thank you very much for your attention.